Good afternoon, everyone. I'm Andrew Mieleniewski. I'm head of technical sales at Briggs. Welcome and thank you for coming. I'm going to talk about electrifying drinks production. Obviously, in an electric brewery or distillery, there's no CO2 in flue gases to recover. So, apologies there. So, access to renewable electricity offers a great opportunity to substantially decarbonise drinks production processes. I'm going to show a slide later on, but in all regions of the globe, the next few years we'll see greenhouse gas emissions for grid electrical power drop significantly. And conversing your process heating from fossil fuel to electricity is an effective way of reducing carbon emissions. Notice I haven't said cost-effective way, but it's certainly an effective way. We'll talk about costs as well. Carbon intensity of grid electricity, quite a lot of data to unpick, lots of local factors. Japan, you can see maybe there was an accident at an atomic power station that shifted them from nuclear. But generally, I think it's clear that the trend is downhill in terms of the carbon intensification or intensity. And within the EU, there are targets to get down to 100 to 150 grams of CO2 per kilowatt hour by 2030. UK has a target of 100 grams of CO2 per kilowatt hour by 2030. You can see we're trending in that direction. Should just say for reference, fossil fuels, they have carbon intensities depending on the fuel and how it gets to your particular site of between 250 and 400 grams. So that sets the area. So again, electrification in all parts of the world does not make sense now. You shift from a carbon or fossil fuel with a lower carbon intensity to a grid electricity where you're generating electricity from coal and your carbon intensity CO2 emissions would actually go up. So, but depending on where you are and the trend, it's generally in your favour. Particularly where, if you look at countries where the percentage of their grid electricity is substantially renewable or nuclear, Norway and France, those CO2 intensities of their grid electricity are really quite low. So we're at 200 with a target of 100. The rest of the world not doing so well, but to say the trend is clear which way that's going. So how do we use that electricity in the process for heating? Very simple. First row, people have been doing that for years. Electric heating elements, kettles, etc., etc. You can do that on an industrial scale. Known technology. Few installations that we used where we're using thermal oil, a thermal oil heater to move around the plant. But on a larger industrial scale, we were wanting to use the advantages of the steam distribution, which usually our customers already have, and changing over their boiler to either a resistance or a high voltage electro boiler. And then just looking at electric boilers in conjunction with steam distribution, it's important to note that the efficiency of an electric boiler is typically much higher than for a fossil fuel boiler. I mean, they clearly vary on loading, but a fossil fuel boiler, 80%, 85% efficient, might drop off considerably if it's not fully loaded at a sufficient point. But an electric boiler, I say, working at its operating capacity, typically 99%. When you turn them down, it's true the efficiency does drop off, might drop off to 95, 94%, but you compare that with fossil fuel boiler operated at 50%, your efficiency may be down at 65% or so. So considerably more efficient. So worth considering how using that technology to do an instant improvement in carbon efficiency and energy use. So here you can see this example is a malt whiskey distillery, specific energy use of 8 kilowatt hours per litre of pure alcohol, dropping to below 7 just by changing the boiler plant. Electric boilers, really quick to start up and ramp up. Often have a really compact footprint, like a vertical configuration rather than a horizontal configuration, which can have advantages. And here's an example. This distillery in China, recently commissioned, designed by Briggs. Steam-powered, steam distribution system, but from a high-voltage electro boiler. Local grid electricity there comes from hydropower on that industrial park. So that is a fully decarbonised facility powered by renewable electricity and high-voltage electro boiler. But. Fuel switching can have a cost penalty. The problem is that in most parts of the world, grid electricity is currently more expensive than gas, 3 to 5 times. So a little bit bizarre to get my mind around in an environment where we're trying to decarbonise, that actually there's a big cost penalty and a big financial incentive to use fossil fuels, but that's where we are. Demand for grid electricity is likely to remain high. Now, we talked about private wire, saw that example in China. Local sources of renewable electricity might change that balance. This is the cost ratio for electricity to gas, but it's very similar for green oils, etc. So we can potentially decarbonise in the long term by changing to electricity. We get efficiency benefit by changing our boilers over to electric boilers. But really, to overcome the cost disadvantage at the moment, we really need to make the electricity really work for us. And that's where the application of heat pumps comes in. So heat pumps as I've said here, help overcome the fuel electricity cost ratio penalty and make each unit of electrical energy go further. We talked a year or so ago about heat pumps and how they use electrical power to move heat from one side of the heat pump to the other, and the ratio of the heating to the electrical work that goes in is the coefficient of performance. And typically for a heat pump, it can be between 2 and 20. That's a very big range. But even at the lower scale, what 2 means is 1 unit of electricity gives you 2 units of heating output. And clearly, CIP of 20 means that 1 unit of electricity gives you 20 units of heating output, which obviously sounds and is much better than the coefficient of performance of 2. But 2 still stretches your kilowatt hour of electricity by a factor of 2. And what I'm going to talk about is 2 examples of high temperature heat pumps applications from within our group. The first is a system concept from our sister company Siemens, which is a waste to energy combined with mechanical compression heat pump for brewery process heating and cooling. And the other example is Briggs thermodrive system, which is our mechanical vapor recompression heat pump technology for distillation heating. So 2 examples, one in brewing and one in distilling. So this is the Siemens Zero system. So heating the brewery and cooling the beer with CO2 neutral energy source, brewers' spent grains. So we have all the heating applications within the brewery. Obviously, the brew house being a major one, but CIP, heaters, deaerated water, packaging, etc., etc. And then we have all the cooling uses, the vessels, piping tanks, process chillers, etc. Brew house generates spent grains. Spent grains vary a bit, but typically about 80% water on a weight basis. We all know spent grains can't be stored for very long, they go off very quickly, get very smelly, so you've got to do something with them. Typically they go away from animal feed, but in this concept we are going to dry them down to 20% moisture. They're then stable in that condition, can be stored for a relatively long period of time. And we're going to do one more step to them. We're going to mill them. We're milling them to improve this, or increase the surface area, so they burn better. And then they're going to be burnt and provide a pressurized hot water system with a temperature of 125 degrees, so that is at a steam or near steam distribution temperature, so it means that this plant is not radically different from what you might expect. And clearly we need to provide energy for the dryer, and here we're using a heat pump. That heat pump is using for its heat source the refrigeration energy that we need to take out of the refrigerant, and then we're boosting that through the heat pump to 90 degrees to power the dryer. And a heat pump in that configuration will have a coefficient of performance of between 2 and 3, probably around 2.5, perhaps a bit more. That type of heat pump, typically double cascaded mechanical refrigerant-based systems, they're available. You can buy those from supply. None of this is novel technology. It's just combined together in a different way. Drying the grains, burning the grains at 60 megajoules per kilogram of dried grains provides us 14 megajoules per hectolitre of heat, which for a modern, well-designed distillery will be what they'll be targeting at. And the heat taken out of here will supply most of the refrigeration. Perhaps a little bit more is required. And you should notice that electric, whatever. So this is an electric system with no fossil fuels being burnt to power this. So this example, 2 million hectolitre brewery, 25,000 tonnes per year of spent grains. We get most of our cooling energy, we get all of our heating energy. There is a shift to some more electricity. Now, there's a cost penalty. So it's all an overall cost reduction, but not as much as it would be if the two fuels, were the electricity and gas in this case, were the same cost. So on current for the UK, that would be a 31% reduction in energy costs and an 80% reduction in CO2 emissions. But if we extrapolate forward to 2030, and I'm assuming that as we get closer to all our global targets, we won't incentivize people to burn gas. So let's assume this gas and electricity cost parity, whatever level it is. Then in that case, there'll be an 80% cost reduction in this scheme and a 92% CO2 reduction. So a really compelling case, particularly if that cost parity is a result of costs going up. Brewery example, distillery example. We'll talk about our thermodrive system. That is part of our suite of heat pump and energy recovery systems for distilleries. Thermodrive is our mechanical vapor recompression system. How that works is it combines falling film condenser, separator vessel, a steam compressor, and an external still heating unit to recover the energy from the distillation hot still process. I do like, as my colleagues know, a Sankey diagram. So the width of the lines in this diagram represent the size of energy flows. So the pot still, typical pot still, driven by internal heating systems, coils, pans, radiators internally, but the energy from the steam goes into evaporating the contents. That goes up the swan neck. Some of the heat is lost as part of the reflux process, which is an essential part of what the distiller is trying to do. But the majority of heat in that distilled vapor needs to be taken out to condense the spirit. And that's typically done by recirculating cooling water through the condenser. That cooling water picks up heat, hence the bar increases. Then we need to dump that heat, so we use a cooling tower, and we dump that heat to atmosphere, and the cooling water goes back around the system. And you don't need to be a chemical engineer to see that, apart from the losses or whatever, that most of the energy from the steam here goes to atmosphere, which could be counted as a waste, unless you like non-whiskey, which I do, so I can't think of it as a terrible waste, but certainly from an energy-intensive nature, it is quite a waste, particularly as this distillation process probably represents about 65% of the energy that's used on this particular site. So what we're going to do is the process stays the same. We'll slightly change the condenser technology. It's called a falling film condenser, which means rather than solid tubes of water picking up heat, there's a thin film of water running down them. And what we're encouraging, the heat from the distilled vapor to cause a fraction of that water to evaporate. And you can see that here, although it's a small part by mass, it takes away a substantial amount of heat from the system, and we get two phases coming off. Water as a liquid and water as a vapor. We take the vapor off in a flash separation vessel, and we recompress that in the compressor to produce low pressure steam. And we use that low pressure steam, compensate for the fact it's a slightly lower pressure than in the previous example by increasing the area. And then we use that in the pot still to heat the process. Now, it's not a perpetual energy machine, clearly, because we need to keep the heat going around the system, and we do that by putting electrical work through the compressor into that steam. So you can see it's clearly a heat pump, moving the heat from one part of the heat pump to the other using the electrical work. Coefficient of performance, so the ratio of steam heat to electrical work in the compressor. It's a batch process of boiling off alcohol, so it changes over the run, has to work harder at the start, 7. Towards the end, temperatures are much higher in here, so the compressor has to do less work, so the COP goes up to 20. What's really interesting for the end user is what the average is, and the average COP works out to be between 10 and 12.5, which equates to between 85 and 90% energy savings in the system. So that COP, I said, averaging about 10 to 12, compared with that previous example where the COP was between 2 and 3. In this case, almost everywhere in the world, you'll have a good and substantial payback with that sort of COP. Which is why we really like this system. High energy efficiency, greater than 85% savings. It's good paybacks, even if the cost of electricity is high. Again, because the payback is high, it means even if it's a really difficult installation, we've got to change equipment around to retrofit it, it's still going to be a decent payback at the end of that process. It's not on the margin of profitability. Clearly, those sort of energy savings generate quite substantial decarbonisation. Put the electrification angle on that as well. That can be a benefit. The system, when we went into designing this system, we compared it with some of the other systems on the market, and we've chosen a single compressor unit. Is it absolutely the very highest efficiency we can get? No, it isn't, but it's a single unit. It rotates slower, it has fewer moving parts, because this is what customers were saying. They're happy with 85% energy savings. They prefer to have trouble-free operation rather than 87% energy savings. So we're listening to that in the marketplace. And the other thing, we have shamelessly badged it up as a system, as a package that a customer can buy with after-sales support and a single point of contact, both to buy, configure, install, and most importantly support afterwards. Clearly this is going into distillery, so it's got to be still house friendly. Lots of distilleries, the still house, the copper stills, they park their visitors' tours, so we don't want a huge rumbly compressor in the corner, so it's got to be low noise, so it's enclosed in an acoustic enclosure. And the other thing is it's fully ATEX compliant, so we can actually put it in the still house, it doesn't have to go in a remote building. It doesn't have to change all the light fittings around it or whatever, so they're all, as I say, still house friendly. Not desperately small. I can assure you, Ben is a normal sized. And also, we've got to find space for it in the distillery. So this unit here is for Mieleniewski distillery. The 2 units going in there. They are literally the other side of this yard in that building over there. They're waiting to be shipped up to Mieleniewski to be installed in their still house there. So inside this unit is a 132 kilowatt motor. So quite a big, substantial motor, but that motor is generating a megawatt of steam. Variable speed drives, you see we'll ramp that down as the COP increases towards the end of the run, so the electrical demand will drop off, but motor rating 132 kilowatts. You see the 2 units. For scale, the external plate heat exchanger that gives us that extra area, which means we don't have to boost the pressure so much, so it means the efficiency of the system is slightly better. Again, we don't want to, typically condensate is driven back to the boiler house using steam pressure, and again, I'm generating that steam pressure through the compressor, so I don't want to do that, so the actual condensate pumping, we have mechanical pumping units for the condensate rather than relying on the steam pressure. You can see those units which were being finished off the other day. And our single point of contact. What does this mean for Mieleniewski? Well, currently they're operating at 8 kilowatt hours per litre of pure alcohol. We are confident that they will get at least a 40% reduction in their specific energy use by just converting their wash stills. In a whiskey distillery, you have wash stills and then you have the spirit stills. So there's an opportunity at a later date to look at putting the same equipment on their spirit stills. We haven't done that because one of the issues is we're maxing out their electrical supply to their site. They've been told they need to wait 18 months to 2 years before they'll get the electricity to enable them to do that. And they need to wait 3 to 5 years if they were going to go down a high temperature heat pump route with a coefficient of performance of between 2 and 3, which would give them similar savings, but would mean a reduction overall in energy use, but a big increase in their electrical power requirements. So say 65 2/3 of their energy saved, but without waiting that period of time until we get that big electrical supply. So you can see that this gives us a decarbonisation roadmap, if you like. Install an electric boiler with the efficiency gains you have from that. That may or may not put you on parity on your CO2 emissions, but as the electricity specific emissions reduce, that will increasingly give you decarbonisation benefits. And then if you combine that with a high efficiency, high COP heat pump system, such as what I've described there, or in that Zeeman system, okay, they're using a lower COP heat pump, but they're using it to dry grains and then burning the grains and then liberating that energy, so they feel like they're getting a boost from it. In that way, you can decarbonise and you can make substantial financial cost savings as well. So really just summing up, lower emission electricity, obviously opportunities to reduce distillery, brewery carbon emissions. Lots of proven electrical heating technologies exist, and they will offer thermal efficiency advantages over conventional technologies. Okay, here's the graph. Typically, cost more to use electricity. So really, to make this work, you need to focus on reducing the amount of electricity you need to improve your energy efficiency of your system or your recovery. Heat pumps are one of the, we think they're the biggest technology that complements this strategy. Just to remind you, we presented two examples, one for a brewery and one for a distillery.